Hi guys, BuildZoid here, and today we're going to be taking a look at the Strix X570i Gaming from ASUS ROG. And this is a Strix motherboard where I feel like it actually fully deserves the ROG name. Which is, like, to be fair, I think some of the other, like, there's other Strix motherboards, like, recently, I'd say there's actually quite a few Strix motherboards where it's like, oh, these don't suck. How surprising. But yeah, this one definitely is just like, this totally deserves the ROG name. I'm a bit of an ROG fanboy. My first motherboard was a Rampage 4 Extreme. I still love my Rampage 4 Extreme. Like, I'm never letting that board go, because that is a great motherboard. Didn't like my Rampage 5 Extreme very much though. Kind of wish I got my hands on one of the Rampage 6, like the what is it? The Rampage 6 Extreme Omega Encore, I think it is. That board, I'm really interested in that one. That one looks really cool. But yeah, anyway, back to this thing. So yeah, I do actually like ASUS. It's just sometimes they put out motherboards where they're not terrible, they're just like, I was expecting better. Especially since, like, you know, if you're, like, I feel like if you're a fan of something, you should actually have even higher standards for it than other people. Where it's just like, but I'm used to you guys making the best stuff, not just good stuff. Anyway, let's talk about this thing. So, the reason why I feel this really deserves the ROG name is because this keeps the very best part, most of my favorite part of the impact, which is, of course, the VRM. So we've got a 1, 2, so that's your phase split right there. So that's our SoC VRM up here, 2-phase SoC. We got our 4-phase vCore, which, again, like, this is basically, like, technically ASUS could run an 8+2 at this point, because Infineon does make a 10-phase controller, but I can understand that, you know, well, I mean, I still wonder what it would, how the performance would be if they just used a proper 10-phase. Like, that would be, well, for one thing, they could get rid of a lot of these input filtering capacitors, because that's kind of the thing with this motherboard. So, the controller on this is the ASP 1405. And this motherboard is like the clearest example of why you normally don't do, like, why most motherboards try to, like, higher end boards have more phases. Because if you had more phases, all of this wouldn't be necessary. As far as I can tell, all of those capacitors are just 16-volt capacitors for filtering switching noise on the 12-volt power plane for the VRM. You know how you would have less switching noise if you had more phases, but this is, like, the controller can't do more than a 4+2 unless you use doublers, and ASUS already, you know, they've already made their stance on, like, doublers cost money, and they lead to very slight delays in your PWM signal, which do translate to potentially slightly worse. Well, not potentially, like, they straight up, like, if you take a design with doublers and then just take the doublers out, you get better transient response. Now, the thing is, you can also design around the doublers to get the benefits of having doublers and also good transient response, but I get that, you know, okay, you don't want to bother with that, cool. But the thing is, with this board is just like, yeah, so you got a 4+2 phase, which, and, you know, they could have run a 4x2+2, so that would have been the 8-phase with doublers, but yeah, so ASUS doesn't like doublers, so their solution to the whole issue of, well, we don't got a lot of phases, and what I think is even a bigger problem on this motherboard specifically is, so on the ROG boards where they do this, they normally use 400 nanohenry inductors, which is really high for a really inductor on a modern motherboard in general. So for comparison, you know, EVGA and Gigabyte, like, they like their 150 nanohenries. Then you have, like, ASRock, MSI generally use around 220. And ASUS uses 400 nanohenry inductors. Now, if you put them in parallel through your power stages, then you effectively get an inductance that's like 200 nanohenries. So it's like, okay, that's totally viable. So you can sort of work around that by putting them in parallel. But the problem with this board is these are small inductors. And the thing about small inductors is that you run into like you basically have a trade-off to choose. Like you basically have a trade to make where it's you can have more inductance and less current handling capability, or you can have more current handling capability and less inductance. Considering that these are 70 amp smart power stages, I'd have it at, like I'd guess that these inductors lean more towards the current handling side of the spectrum. So I would guess they're probably somewhere between like 200 nanohenries and 300 nanohenries, which means any one of these phases is probably below 150 nanohenries when it turns on. And that, like, the thing about having low inductance inductors is that translates into more switching noise on the 12 volt power plane because the current ramps up faster through your phase when the phase turns on. Now you can compensate for this with higher switching frequency again, but that very quickly leads into more heat output on the actual MOSFETs. So you don't necessarily want to do that, and the easiest solution is just throw more input filtering capacitors at it. Which the funny thing is, if every single one of those, because again, I'm not sure, maybe one of them is a 6.3 volt for the USB, but I think that's mostly just these guys for the USB ports. But if like this is more input filtering than what you would get on say, well, Gigabyte's X570 Extreme is kind of special because it has a 14 phase V-core, so it's like you really don't have that much ripple to start with. But yeah, this is like twice the input filter for that board. Or if you look at the Crosshair 8 Hero, this is actually one capacitor more than the input filter on that motherboard. And really, if you just look across like a lot of various X570 boards, most of them will have somewhere around 4 input filtering capacitors, not 8. So about half the input filter of what this does, because low inductance inductors, or, well, I'm assuming well, no. If it was one inductor per phase, it would be completely normal. It's just that if you have the two of them in parallel, it effectively cuts the inductance in half. So your current slew rate is doubled. That's where you get the switching noise problem. So that, like, basically very low per phase inductance, low overall phase count, and, well, this is the easiest way to solve that. That doesn't involve using a bunch of doublers, because if you used a bunch of doublers, your inductance would have effectively double, because you wouldn't be turning on two phases at the same, like 2 power stages on at the same time, and so connecting 2 inductors to the 12 volts at the same time. Yeah, so, you know, yeah, this is kind of the whole the trade-offs of running a low phase count, where it's just like you just need more input filtering to deal with it. And yeah, so ASUS just basically decided, yeah, this is a trade we would rather make compared to, say, running a bunch of doublers, which is like, fair, whatever. I don't actually really care that much about the input filter, and with this many capacitor, I assume this works just fine. Because the thing is like, yeah, you can literally just sort of brute force some issues like this, where it's just like, well, got a lot of switching noise, throw more capacitors at it. Solved, right? It's just that really, like, some other board vendors would just go straight for doublers, and then it's like you don't need as many capacitors then. But anyway, different design philosophies for the different, you know, vendors. So, and I really like, well, it's a good idea to have a low switching noise, because obviously that just puts less load on, like, the PSU, and also the actual capacitors. Like, the thing is, if you actually ran this board with less capacitors, yes, you'd have more switching noise, but also the current going through each of the capacitors, like the ripple current through the capacitors, would be higher, which would mean the capacitors would potentially run warmer, which would potentially mean that they last a shorter time period, though they're all probably rated for 10,000 or 5,000 hours anyway at 105 degrees Celsius, so probably not an issue, like, wouldn't really be a major concern in the first place. But still, yeah, this is kind of like, we have, you know, high-end, like, well, no, most motherboards don't have this much input filtering. This is just like, this is how you deal with these kinds of issues. Anyway, you know, what I'm much more interested in is the output filter, because this is the part that really tends to make a huge difference to your CPU overclocking. And in that department, we all know I love these. If you've been on this channel for long enough, then you know I love these, because those are SMD aluminum polymers. Now, the funny thing is, you can actually get cylindrical aluminum polymers in an SMD package as well, so that you can use surface mount assembly lines to do them. but they're still cylindrical. And the cylindrical packaging of the aluminum polymers is just inherently worse than if you use the SMD style, where it's like these flat ones. So, and especially when you have 3 terminal ones. So basically you have positive on this end, and then you have ground here, and you also have a great big tab right down the middle, which looks kind of like this. And that's just more ground. And the cool thing about these 3 terminal ones is they are very, very low equivalent series inductance, which basically means they work much better at higher, sort of like filtering out higher frequencies. So yeah, these are absolutely awesome. Now, the reason why you don't see them on like high-end ATX motherboards is they cost a lot of money. They're generally 2 to 4 times more expensive than, well, that's the thing, like, they're just like, well, yeah, like the typical aluminum polymers that a board vendor would actually, like the cylindrical polymers that a board vendor might use. So yeah, 2 to 3 times more expensive. You also can't get them in high endurance ratings. Generally, you're going to be looking at 2,000 hours at 105 degrees. In my opinion, that's really not an issue. Just design a VRM that never gets above 60. There, problem solved. You can now use superior capacitors. So yeah, like electrically, these are great, but they're expensive and you can't get them in like super high endurance ratings. And I think a big thing for a lot of board vendors, like a big thing with the capacitor endurance ratings is just it's easier to market that a capacitor has 10,000 hours worth of endurance than, you know, putting the frequency response curve for this capacitor against like an aluminum polymer on, well, a cylindrical polymer on the motherboard box, because let's be honest, most people would look at that and have no idea. I mean, most people look at the hour rating and probably have no idea what that means either. But, you know, hours are a simpler unit than like ESR or ESL or really anything like that. Though it's funny, sometimes you see marketing on motherboard pages where they're like low RDS on MOSFETs, and then you actually look up the datasheet for the MOSFET and it's like, yeah, I mean, yes, you could definitely find higher RDS on MOSFETs, but those would be really, really bad at that point. And it's not like the ones that are actually on the board are that great in the first place. Yeah, but anyway, I'm a huge fan of these because basically these are great for output filtering. They're just kind of expensive, and you generally see them only used on ITX boards and other small form factor motherboards because, you know, for like you physically couldn't fit a cylindrical polymer on a board like this. Like you just like this is literally inside the mounting space of the heatsink. Like if these capacitors were any taller, you wouldn't be able to mount a heatsink. So that's kind of the main reason that why these are restricted to ITX boards, which I think is a shame because I would like. Well, we do sometimes see, you know, ATX boards where these are like SMD polymers are used, but a lot of board vendors tend to avoid them because, as I said, expensive and kind of hard to market, right? Most people have no idea why these are better. And probably me explaining this, like, you probably still don't have any idea why these are better, but they are, trust me. I've actually measured it. They're great. They're absolutely amazing. Shame about the endurance, though. So the other thing that I'm actually a big fan of with the capacitors here is that they're also jammed right up against the socket. So the closer you can get your output filter to, well, so basically these are both used for filtering out the switching noise from the VRM itself, because obviously, you know, it switches on and off. So that produces switching noise, but they're also there mainly for dealing with transients from the CPU. And, well, the closer you put your charge reservoir to the thing causing the transient, the better. So, yeah, I'm a big fan of the fact that these are just crammed right up against the socket, even though that's really just a side effect of how this motherboard is laid out, right? Like, that's really just like they couldn't fit the capacitors anywhere else. But, hey, I mean, like, we saw something like I saw something similar with the ITX from Gigabyte, where that board just kind of beats everything else on transient response within the same price range, because Gigabyte was forced to use the better capacitors because they couldn't physically fit the larger, cheaper ones, and then they had to jam them right up against the CPU because there's just not enough space. And it's like, well, I mean, it might not be intentional, but I'm still a big fan of it. Right, like I'm certain if there was more space on this board, we wouldn't be seeing these. But hey, there isn't more space, so I'm a big fan of aluminum polymers. Now, so these are the ones for the V-Core here. If you're wondering why I didn't highlight like these ones, those are for the SoC VRM. And again, they help the SoC, but the SoC isn't really like a high current rail. And, well, I have my doubt. Like, I really don't think it cares that much. Like, if it was on the slightly inferior, not slightly inferior, but, you know, if it was on the sort of standard SM cylindrical through-hole capacitors. So, yeah, anyway. So basically, we went over the control scheme. So the only thing left, so, you know, we have the output filter. It's not laid out the same way as it was on the on the Impact, which I think, like, that's actually, I assume the sort of, like, if you look at the Impact's output filter, it has a really specific capacitor arrangement. It's a bit more than just jamming as many capacitors as you could physically fit between the CPU and, like, the socket and the VRM. And on that board, I really think that's like a further power plane ESL optimization. But here it's just like, well, these are still great capacitors and they're really close to the CPU. So, hey, I'm a fan of that. And yeah, so I'm really like, these are nice to see, right, from the Impact as well. And the other thing this copies from the Impact is the power stages. And this is like, when I saw these pictures, I was super surprised because I thought this was on the 50 amp, power stages from Vishay Semiconductor. And they're powerful, but they're not smart. They're not the most efficient thing ever. And I mean, they're very efficient, but they're not, it's not on the same level as a 70 amp smart power stage. No, so this uses the same power stages as the Impact, and those are the TDA 21472s. And good luck finding a power stage that, there's actually power stages rated up to 75 amps in the, like, that are smart power stages. But the thing is, they're very, very expensive. And I don't think I've seen a single GPU or motherboard use them. So that's kind of the thing, is just like, as far as motherboards go, you're really not going to see anything better than these. And these are freaking awesome. So I'm a huge fan of this VRM, because with 8 of these in parallel, you get, like, the thing is, the main the main issue with VRMs on motherboards and GPUs is getting the low side RDS on as low as possible. And if you just put a bunch of stuff in parallel, you achieve that very easily. Like, that's one place where the doubler really doesn't make, it can lead to slightly better efficiency because you can better current balance the phases. But it's not it's not super necessary. And you might only be losing a couple percentage points worth, couple percentages worth of, like, heat output, not actual the efficiency itself. The efficiency is still going to be, say, in the 94% range or 93% range. I can't remember where these actually top out right now, but these are super efficient. And having a lot of them means, yes, this VRM is super efficient as well. And it's actually like the same configuration of power stages as what you see on the Impact. So this thing is absolutely freaking awesome. Like, this is, like, if you want to run a 3950X on ITX, this board, this board right here, 3900X also, sure, go for it. 3700X, this is super overkill. 3800X, super overkill. But yeah, for the higher core count CPUs. The other thing is ASUS actually has a fan integrated into the VRM heatsink for this board. There's another fan for the chipset down here. So they somehow managed to squeeze 2 fans on this. But since they have a fan in the VRM, so not only do they have, I think this is straight up the most powerful VRM on ITX that you can get for X570, but they also have a fan. And the thing is, fans are overpowered because convection is a crap way of trying to cool something, because hot air, yes, it rises, but it rises very slowly. And so it does, like, it's awful at actually getting any cooling done. Fans, however, they push air quite forcefully. So, a fan, not even the biggest fan, not even spinning that quickly, can make a huge difference to VRM thermals. And so, yeah, like, as far as cooling goes, as far as VRM power handling capability goes, this board wins. It just wins for X570 because you have the integrated VRM fan, and yes, everybody else also has the chipset fan, but it's like, I kind of wish that some of the other board vendors had, like, put like a VRM auxiliary fin stack right against the chipset fan, so that fan can like cool both the VRM and the chipset. But yeah, like they're kind of doing that, but it's not super prioritized. Whereas Asus is just like, put a fan here, put a fan there, so thermal's sorted. Don't need to worry about that anymore. So yeah, I'm a huge fan of just like this VRM in general. Like I love this board. In fact, I like this board so much that I've been considering not bothering with getting the Impact, because I'm probably not going to run I'm probably not going to end up running the Impact on LN2 anyway. And I still want an Asus motherboard to do like BIOS walkthroughs and memory, like do some memory overclocking on X570 Asus boards. So yeah, it's just like I'm thinking probably going to pick up this because I love that VRM, and yeah, it's much cheaper than the Impact. And you don't lose, you lose all of the extreme overclocking features, but you kind of keep all of the necessities, which, is why I'm such a huge fan. Anyway, let's talk about the efficiency at last. Somebody's just like, Buildzoid, I just want efficiency figures. If you just watch the Impact video, I give them away there as well. I mean... So yeah, if you saw that one, you're not going to see anything new here. So 1.2 volts output, 400 kilohertz switching frequency, and of course 5 volts drive voltage, because that's what those power stages run on. You're going to be looking at 100 amps output at about 8 watts of heat coming off of the power stages, which is nothing. As a general rule of thumb, if your current output can be divided by 10 and that's still that's higher than the heat output, the VRM is really efficient. Okay, like if 100 divided by 10 is 10, so yeah, 8 is less than 10. This is very efficient. So yeah, but it gets better because these actually, these are 70 amp smart power stages. They are very overkill for, 100 amps output. Because I think Asus really prioritized designing their ITX boards with like the 3950X in mind. And yeah, this nails that. So 150 amps output. 11 watts of heat, and 200 amps of output, 16 watts of heat. The 3950X at totally unsafe for long-term use voltages at completely is utterly uncoolable at this point. Like if you're trying to do ambient, 200 amps going into a 3950X, you're looking at 90 degrees plus on the CPU cores, pretty much regardless of what cooling system you throw at it. So actually potentially like 100 degrees plus. Like it gets really hot. So, and somebody's like, wait, Buildzoid, you have a 3950X? No, unfortunately I don't. But I did get to play with a 16-core engineering sample, and those ran really, really hot. And I like the main difference is like the 3950Xs will clock higher, but they're not really going to change the power. Like the per voltage power consumption isn't going to change a whole lot. So anyway, 200 amps, 16 watts of heat. Like, you could max out a 3950X on this board. At this point, maybe the fan in the VRM heatsink might start like being audible, but still, it's just like 16 freaking watts at 200 amps. It's awesome. Absolutely freaking awesome. Like, I love this VRM. Like, there's a reason why it made it onto the Impact, right? So you can't really be surprised that it's freaking, like, it's so great here as well. So anyway, going past that into like extreme overclocking territory, which really isn't where you should be running this board. 300 amps, 29 watts of heat, right? So I think this VRM actually hits its peak efficiency in this range. So yeah, it is very much, designed for 12 plus cores in terms of overclocking capabilities. And then 400 amps output, that's when the VRM really 29 watts is a concern here because this is very, it does not take up a lot of space. It's a very dense little VRM. So, 29 watts of heat, kind of a cooling problem. 48 watts of heat, not kind of a problem, definitely a cooling problem. Luckily, there's no way you're ever getting any CPU on AM4 to get anywhere near that with ambient cooling. Like, honestly, even getting near 200 amps on ambient is really, really difficult. At least if you like your CPU not running at insane temperatures. So that's kind of the thing, is just like, yeah, this VRM is freaking awesome. And that's why I like this board so much. It's just like they took the best part of the impact and then made it cheaper. I mean, what's not to like, right? So yeah, I'm a big fan of this. So that's the VRM, and we really don't need to go any higher than this because it's not really relevant. I guess let's go over the... Oh, well, SoC VRM is just more TDA 21472s, but I don't really feel like getting into that because, quite frankly, it's an SoC VRM. It's a two-phase. It's got 270 amp smart power stages. We all know it's totally overkill, and that's all that's necessary to know, right? Like, the SoC really doesn't need to put out even more than, like, 20 amps at most. So, yeah, like, SoC is totally fine. Nothing to complain about there. Nothing to really talk about there either, because it's just going to be like, oh yeah, it produces very little heat. Anyway, noteworthy features around the board. You have a CPU socket thermocouple hole. So if you did want to run LN2 on this board, you could still, like, that's... Like, the funny thing is, ASUS actually has the thermocouple hole in I think every single X570 motherboard they made, which I'm not sure what the logic behind having it there is. It might be that they just designed their like capacitor configuration for the CPU socket once, and then they just copy paste it around, and the hole is just part of that that layout of the board. So it's just like, yeah, the hole stays because nobody could be bothered to remove it on the motherboards that don't need it. Like, I really like... Actually, this might still have all the necessary voltages for extreme overclocking, so you might be able to run this on LN2, but the thing is, you don't have the postcode, you don't have the safe boot, you don't have the retry, you don't have the power button, the reset, you don't have the LN2 mode. So a lot of the things that really make the impact on LN2 board, those were removed here, right? You just get kind of the things that if you're on ambient, that, you know, the best parts of the impact for ambient overclockers, yeah, it keeps those, except of course the postcode is missing, which is a shame. Yeah, I wonder if they could have... Oh no, there's the M.2 slot. So yeah, there's no postcode. That's like the main downside with this board, is just no postcode. But they did still manage to keep a bunch of troubleshooting LEDs. Now, if I could only... I do believe they're up here, and we just can't see them. So they do have color-coded LEDs for indicating what part of the boot process you're in. So you'll have some idea of if like you failed on memory or CPU or GPU initialization or potentially boot device initialization, right? So it's not it's not as great as a postcode, but it's better than nothing, right? Far better than nothing. And it's also being color coded. It's actually better than a lot of the basic troubleshooting LEDs you get on a lot of other boards, because on a lot of other boards, they're all the same color, they're right next to each other, and they're blindingly bright. So once they light up, you'll have no idea what's wrong. You'll just know, yes, there's an LED glowing. I can't read the inscription under it. I don't know what's actually, I don't know what this LED is telling me, because anytime I tried to read that, yeah, the LED is blinding me. So yeah, the fact that these are color-coded does mean that, you know, you don't even need to look too closely. You just have to remember which color corresponds to which error, and yeah, awesome. So I'm a big fan of ASUS having the color-coded LEDs like that. What else is there? Oh, well, we have the single-phase memory VRM. That's standard. We all know that, like, with the memory, the thing that's really important is what's going on in between the DIMMs and the CPU socket. How you power the memory with, like, DDR4 really doesn't pull that much current, so it's not really that difficult to power DDR4. The main issue is just getting the memory layout, you know, perfect, essentially. That's there. Obviously, it's never going to be perfect because there's always something you could tweak, but yeah, the priority, like what makes the biggest difference is just how are the memory traces laid out, how many DIMM slots you have potentially, right? Where assuming like ITX boards kind of get an unfair advantage in memory overclocking over a lot of ATX boards just because there's less DIMM slots, and that just means the traces are shorter, and well, that's the main thing, is just the traces are shorter, and you also don't have the actual, like, the DIMM, it's like the DIMM slot itself acts as a as well, there's a bunch of unwanted parasitic effects from having a DIMM slot at all. So if you even have like a daisy chain board, just the fact that there are DIMM slots is actually harming your overclocking range. And there are some, like, I've seen some engineering sample like extreme overclocking boards where they would make them with like it would be a daisy chain layout, but they leave out the extra DIMM slots just so that it's like, okay, we got at least some of the parasitics from the DIMM slots removed by just physically not having them, but you'd still have the same trace length as a normal daisy chain. It's just that the DIMM slots were gone. So yeah, ITX boards, assuming that there's nothing like the funny thing with ITX boards though is that obviously because they're so cramped, there is the potential for, say, a fan header to randomly find itself in the middle of your memory, in between the memory and the CPU, which is of course not ideal. But I have faith in ASUS doing like a good memory layout on a board like this, which, you know, I don't really, I wouldn't say you should trust vendors based on brands ever, but I'd be surprised if this was actually bad at memory overclocking. Okay. That's not to say I think this is like, I'm not saying this is a great board at memory overclocking. It's just, I'd be surprised if it wasn't. So yeah, because it is, you know, it's 1 DIMM per channel. And, you know, at least from the top side, this is relatively clean. We don't really see anything like, yes, you have your memory power up here. It's kind of, and then if we look at the back, well, this is kind of where it's like, there's the RGB controller, but this is actually also present on the impact. So maybe like there's a chance that this actually uses the same memory layout as the impact, because there's a lot of similarities between sort of, well, this area of this board and the impact as well. So, you know, there's actually a chance that you actually get the impact's memory layout. Though one difference between this and the impact is that the impact actually uses tantalum polymer capacitors for its memory output filters, and these just look like regular aluminum polymers. So yeah, I wonder if there's any significant difference to that. I think also the output filter in general here is a bit reduced in size, but I'm not sure that would make much of a difference. I guess it would depend on what kind of DIMMs you're running. Maybe if you're running something that really pulls a lot of power, it might start to play a role. But I kind of doubt it. I really think, like, you know, I would be very surprised if this was bad at memory overclocking, though I'm still not a fan of the fact, like, the RGB controller sitting in the middle of the memory, in between the memory and the CPU is just like, well, it's kind of like the last place I'd like to see that, but sure, whatever. The Impact does that too, and the Impact has posted some incredible memory overclocking results already. So yeah, wait a minute. No, this capacitor layout is new. Unless this is also copied off of the Impact, which it might be. Anyway, these are kind of neat. Those I assume are actual tantalums. Those could be very, very, like, so, like, I'm not sure what they actually are, but yeah, I guess they didn't have enough bulk capacitance in the main vCore VRM, so these are kind of acting as backup. Though the funny thing is, you can actually get these in specs that are very, very similar, like ESR, ESL-wise, very, very similar to like high capacity multi-layer ceramics. So like a 47 microfarad multi-layer ceramic, you can actually get tantalums that are very, very similar to those. Admittedly, those tantalums are insanely expensive, especially considering that the capacitance on them really isn't that high. It's higher than the multi-layer ceramics, but crazy expensive little capacitors. But yeah, these might be some of those. These might just be like, oh, we didn't have quite enough bulk capacitance. So yeah, I'm not sure. Like, they're just interesting to see, because you don't really see a lot of motherboards using them. Like these very small tantalums. So yeah, you know, these might further improve the transient response of this board. And anything else on the back? Not really. I mean, we talked about the probe hole. That's kind of the thing, is like, this is really an impact. Like this is, yeah, in my opinion, or at least as far as I can tell, this seems to basically be an impact with all of the extreme overclocker stuff taken off, except like the probe hole. Right, the probe hole is still there because I assume it was just like, well, who cares about, you know, filling it in? I guess you could fit one more multi-layer ceramic where that hole is, and really that probably wouldn't make any difference. So who cares? So yeah, I'm a huge fan of this board. Like, I cannot overstate how much of a massive fan I am of this board. Like this VRM. This output filter, 1 DIMM per channel, you know, and it looks a lot like the Impact memory layout. Though, interestingly enough, I do believe the Impact is actually branded OptiMem 2, and this is branded OptiMem. The funny thing is, that might just be to get people to buy the Impact instead of this. Like, I wouldn't be surprised if that was actually the case, where it's just like, oh no, we'll just change the branding instead of actually changing the physical layout of the board. Because this looks so Impact. Especially from the back, where it's just like, I'm like, these capacitors, I'm 99% certain are in the exact same spot. That chip is in the, you know, exact same spot, like relative to where the DIMM slots are and the CPU is. So, you know, if those haven't moved, why would anything else move? Right? That's kind of the thing that I'm thinking with it. So, yeah, this is a really cool motherboard. So, yeah, I think I've covered everything at this point, right? Like, awesome V-core. You're really not going to get a better V-core than this. What else is there? Yeah, that's it. It's just like, yeah, so this is also the most expensive X570 ITX board. And I'd argue, like, yeah, there might be some people where, say, the ASRock board makes more sense than this because you need the Thunderbolt 3. And I guess you could also, you know, the Gigabyte board, you could, like, the Gigabyte board is actually the cheapest ITX board out there. And it's not, like, that still has a 6-phase V-Core VRM using the TDA21472s. It's just that one's heatsink design is a little bit heavy on the aesthetic and less so heavy on the function. So, and it doesn't have a fan built into the heatsink for the VRM itself. So with that board, it's just like, well, this board will be better at running the high core count chips. Like, straight up on the high core count chips, this board just has an advantage. But, you know, this one is also a bit more expensive, so it really depends on what you're trying to, like, I guess, achieve with your build. Well, yeah, if cost is no concern, then this is my favorite ITX board. The main, like, the ASRock board, the main benefit there is that you get Thunderbolt 3, which I unfortunately have no idea why you would use Thunderbolt 3. Well, I think it's like, I've heard that you can use it for eGPUs, but desktop motherboard. So yeah, like, evidently Thunderbolt 3 not meant for me, because whatever, like, I couldn't care less what it actually does. Yeah, so for Thunderbolt 3 users, there's the ASRock board. But if you just want the best VRM in an ITX form factor, because let's say you're running a 12-core or a 16-core, and, like, the thing I wonder about is, like, what will happen with the 16-core when you, like, unleash Precision Boost Overdrive? Because if you take off all the limits, yeah, it might not be as bad as what I did to the engineering sample chips, where I literally just set it to, like, 1.37 volts and was just like, go for it, chip, go. no V-droop, nothing, just 1.37 volts, prime 95. And it was just like, and that was bad. Like, it ran stupid hot doing that. But I would assume that, you know, like, the thing is, PBO, like, it can get up there in terms of voltage. It can go into the low, like, it can go up to 1.3 volts in prime 95, and that's still pretty damn hot. Like, I would expect you to still end up in that 150 to like, in this range here. And so this board could very easily have, like, a PBO overclocking, like an actual PBO overclocking advantage, where it's like, this VRM just runs cooler when you run PBO. So yeah, that's kind of the thing, is, like, I honestly think, yeah, if you're going for a 3950X, like, I would go for this, right? Like, especially considering that, as far as I can tell, this isn't that much more expensive. It seems to be like $30, maybe $40 more expensive than the other ITX boards. So it's just like, if you don't need the Thunderbolt 3, get this, right? That's my thoughts on that anyway. So yeah, I'm super impressed with this board. It's like, yes, we finally get a real ROG motherboard. Well, no, we finally get a Strix board where it's like, oh yeah, it lives up to the ROG branding. So yeah, that is it for this video. Whoa, this one's long. Oh, well, it's a cool board, so what did you expect? So yeah, that's it for this video. Thanks to the fan of the channel who sent in the pictures. because obviously I don't actually have the board myself. I've not yet. I've not yet managed to find it in a store to buy it, though I might just try asking ASUS to send one, because I really do want to get my hands on one of these. Anyway, so yeah, thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support me directly, I have a Patreon where you can do that. There's a link to that down in the description below. And if you don't like Patreon, we do have, there is AHOC merch. There's a bunch of shirts, stickers, posters, socks, hoodies on Teespring. So you can find a link in the description to that as well. And yeah, both of those, like Patreon and Teespring, both help out immensely with running the channel. So yeah, if you'd if you'd like to check those out, that would be awesome. And yeah, that's it for the video. So thanks for watching, and goodbye.